I am Mr. Tarrou. Okay, let's start talking about our basic introduction to probabilities. Chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. Law of large numbers. What do I mean by that? Well, we know that at least if you live in a state or a country or whatever that has a lottery, while someone can win $1 million or millions of dollars based off of just a $1 ticket, the state lottery knows that over the millions, if not hundreds of millions of tickets that they sell, they're going to make an average amount of money per ticket sold. So, you know, they know that there's a regularness to that pattern. There's those extreme wins or an extreme loss for the state on a single ticket, but over the very, very large run of tickets, the law of large numbers will say that over that long run of all those tickets they sell, as long as they gauge the winnings to the probability of winning versus the price of the ticket, they can easily set it up so that they win, you know, that the state makes an average amount of money per ticket sold. And then we have the idea of empirical probabilities. In the last video or set of lectures, I talked about how there's 3 ways to get probabilities. Through just theorizing. I looked at this coin and it's, you know, two-sided in metal, so each side must be 50% chance of occurring. There's simulations where you assign numerical values, if you are randomly generating numbers, to real-life events in such a way that the numbers represent the actual probability of the event occurring, and then you randomly generate those numbers and you analyze how they would act as an actual real probability. And then your final statement is, you know, based on my blank number of simulations, the probability of this event occurring is blank. But an empirical probability is one that is found through actual observation, not through theorizing or calculation, not z-score calculations. You know, we talked about in Chapter 2 where we had normal distributions. We assumed or knew that we had some kind of average, and we calculated through the z-score process of x minus mu over the standard deviation, you know, the probability of observing a given event, knowing that the mean is something and the standard deviation of that normal distribution is something. No, an empirical probability is, you know, something like the casinos will do, where, you know, casinos will have God knows how much money goes through their doors every day. When they get those 6-sided die to come in for their, you know, crap games and whatever, I don't know, I don't gamble, but I do know that they will test those die to make sure that, you know, that each side of that die really does come out to be 1/6 probability out of each side. If you want to see if a coin is fair, a 2-sided coin, that it really does land 50% heads and 50% tails, you know, that would actually take a surprising number, like thousands of trials, before you know, get to a consistent 50% heads and tails. You could flip a coin 100 times and maybe have heads come up 45% of the time, and that's really not that unlikely. It would not really show that that coin is unfair just because of the variability of the results. 100 trials is still not falling into the idea of law of large numbers. We're talking very long sequences of trials. And empirical probabilities will, you know, generally take a lot of time and effort to actually observe those new probabilities. But if you want to find what percent of the population are going to vote for a particular candidate, or what percent of your community goes to a certain store or goes to the church or something like that, you actually have to learn those new individual probabilities through observation. We can't just theorize and simulate everything. All right, so moving on. Woo! Alrighty then. So, you're going to hear a lot about law of large numbers with my sort of, again, this outline of topics that I give you. It's not, you know, it's kind of more in depth than you would see maybe at the end of the chapter with your summary of the section notes, but certainly not as good as you really want to, you know, watch these videos if they're helping, and I certainly hope they are, but please be reading that book. Please be reading those examples, or read those examples, and make sure you understand all the little nuances of all the different kinds of questions and what they're going to be looking for in the structure of the response. Again, so okay, a random phenomenon is one whose individual outcomes are uncertain, but there's nonetheless a regular distribution of outcomes in, again, a large number of repetitions. So if we're talking about winning that lottery ticket, or trying to buy lottery tickets to win the lottery, yes, people spend $1 and win millions of dollars, if they're playing the full-size lottery game, but whatever. We gamble. We like to go to Las Vegas or whatever, casinos, and we like to, I don't, but a lot of people do like to gamble and, take that risk, take that chance of winning some money. But the casinos in the states that are selling those tickets or designing those games are going to set them up so that they know over the millions of trials, or hundreds of trials, or whatever, hundreds of thousands of trials, that they are going to win on average. They don't make those games to truly break even. They make those games, those lottery games, casino games, to make money. They give you the tease that you could win big, and some people do, but on average they will come out to be the winner. And that's what I mean by that regular distribution. Or say flipping a coin, a simpler example. You can flip a coin 5 times, get heads 5 times in a row. That does not mean the next flip is going to be more likely tails. That those small individual trials are random. We don't know what's going to be next. 5 flips of a coin in a row and getting heads 5 times does not make the next outcome more likely to be tails. But if you flip that coin thousands of times, then roughly, it's not exactly 50%. I mean, it's an observation, but the more you flip that coin, the more closely your estimate will be, if the coin is fair, to that true 50% heads, 50% tails. And that's the idea of random phenomenon, and again, talking more about law of large numbers. The probability of an outcome is the proportion of times an event would occur, again, very long series of independent trials. So, when you flip a coin, and you flip it again, that piece of metal doesn't know where it landed on the last time. If you flip it and it lands on heads, it doesn't go, oh, I better come up to the tails pretty soon. If you're shooting free throws, let's talk about sports. You're shooting free throws, boom, boom, boom. I'm horrible at basketball, so I'm probably going to miss a lot. And if so, I just stand there, boom, 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 throwing free throws, and I make like 50 shots, that would be assumed. In statistics, we would assume that those trials are independent of each other. And so I could take 50 shots and then say, well, from that 50 shots, I only made like 15 of them, so my probability of making a free throw is 15 out of 50. However, because I'm not good at basketball, I got one of our coaches to kind of help me out, and I take a few shots and he's watching me, boom, boom, boom. All right, well, you're standing wrong. Okay, well, let me change how I stand. Boom, boom, boom. Let's make a few more shots. Your hand posture is wrong, or your hand position's wrong. Okay, boom, boom, boom. All right, so look, behind the ring, the hoop, not right in the front. Okay, so if I'm getting tips on how to make this free throw shot as I'm working through my trials, well then they're no longer going to be independent. And hopefully if the coach is good, my success is going to get a little bit greater through those trials. So that would not set up a good probability. I couldn't go back and say, well, I took my 50 free throws and I made 20 shots out of 50, so my probability of making a shot is 20 out of 50. No, because I got coached along the way. And hopefully at the end, my probability of success is higher than at the beginning, at least if I'm getting coached on how to shoot a free throw. So we do need that independence of repetitions or trials. And the idea of independence is what's going to be repeated now all the way through the rest of the book. All these statistical analysis we start running, z-score calculations, whether it's proportions or means, and we're doing observations from the population, we will need to have independent trials and observations. Now we can also have independent outcomes, but that idea of proving that 2 outcomes are independent of each other will be spoken about and explained in a later video. Probability model. Now we're going to run out of the screen here, so I'm going to have to move here in a second, so this isn't the complete idea, but setting up a probability model. We need a sample space, a set of all possible outcomes. So, alright, I'll explain this further in the next screen, but we need a sample space, S, that is a set of all possible outcomes, and an event, which is any outcome or set of outcomes of a random phenomenon. It is a subset of the sample space. So, even though I'll explain this further in a second, since the definitions are here, if I roll a die one time, I've got, well, if my variable of interest is the number of dots that show up, then I've got a sample space that consists of 6 outcomes, 1, 2, 3, 4, 5, and 6. And an event would be any outcome or subset, or a set of outcomes of a random phenomenon, and that's a subset. So maybe like I want to talk about the probability of a 1. So the event would be getting a 1. Okay? Maybe my event is, what's the probability, that's the ultimate question, what's the probability of getting an even? Well, an event then would be getting a 2, 4, or 6. That would be a subset of the, that would be a subset of the sample space. My sample space, again, if it's just simply the number of dots, would be 1, 2, 3, 4, 5, 6. And if I was concerned with even, probability of getting an even, the event would be an even number of dots. That would be, the subset would be 2, 4, and 6 out of the entire sample space of 1, 2, 3, 4, 5, and 6. All right, moving on. Woo! Shabam! Okay, probability model is a mathematical description of a random phenomenon consisting of 2 parts, a sample space, and a way of assigning probabilities of events. So let's talk about rolling a die one time. Well, then X is the number of dots, and therefore my sample space is going to be X, and I got to list all the possible outcomes based on this definition. So 1, 2, 3, 4, 5, and 6, and the probability of those outcomes, and I'm just going to assume, I'm not going to actually observe this, I'm not going to roll the die thousands of times to make sure that it's fair. I'm just going to assume that it is fair and assign the probabilities as 1/6 across the board. Now, for this to be a valid probability model, I have to include all of the outcomes that fit this definition, and my probabilities must add up to 1. So now I can say, well, the probability of getting a 2 is 1/6. My probability of an even is, well, 2, 4, or 6. So 1/6 times 3, or 1/2. Now, I can also talk about maybe X is, well, you know what? I can hear my alarm going off, which means I have less than 2 minutes left. So this is one example of a probability model. Here's another quick one, and I hope you can read it, it's not too small. If I roll 2 die, that's 6 times 6 outcomes. So that means that there's a total of 36 possibilities. My next video will talk about the multiplication principle, how we know that 6 times 6 is 36. And if my variable of interest is the sum of the dots, not just all the possibilities, which is 36 of them, I narrow it down to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possibilities if X, the variable of interest, is the sum. And then I've listed off the probabilities here. So this would be a probability model for the sum of the dots when you roll 2 die. Roll 2 die, 36 outcomes. But if the variable of interest is the sum, there's only, whatever I just counted there, 6 or 7 or 3, 6, 9, 11. Alright, I'm Mr. Tarrou. Part 2 is coming up very soon. Woo! Thank you for watching. Thank you for letting me help. Bam! Mr. Tarrou! Okay, with the crazy Garfield shirt on. We're going to finish our introduction to probabilities, and we're going to start off by talking about tree diagrams. Now, in my chapter, in my book about probabilities, we will learn some basic probability rules here in a minute. And there's going to be in the next video a set of more advanced probability rules. But even the textbook will say that while we have to know how to use these formulas, how we have to know how to interpret them and read them, we'll actually answer a lot of questions with two types of diagrams, a Venn diagram and a tree diagram. So let's take a look at the tree diagram first. They're fantastic for listing a sample space. Remember, when you do a sample space, that's a list of all of the possible outcomes. And if you have a sequence of events like I have here, where we're going to analyze, and I just came up with these numbers off the top of my head, but they're not too far from the truth, analyzing a student's performance in my class, and then whether or not they pass the AP exam. I teach a lot of seniors in second semester. When we get around to the AP exam, those acceptance letters start coming in, and senioritis hits in. Sometimes they slip a little bit second semester. So my sample space would be 4 possible outcomes. Keeping an A or B average the rest of second semester and passing the exam, keeping that A or B average and not, or letting their grade slip and then still passing the exam or not passing the exam. So there's 4 possible outcomes or tracks to get down there. Now, the best use and the one use that I use for tree diagrams the most are for finding the probability of a sequence of events. Like this example, you have to do well first, and then that will build up your probability of passing the AP exam. So when you have that sequence of events, and you can set that tree diagram and find the probability of that sequence of events, regardless of whether or not those events are independent or dependent. These are 2 dependent events. What you do in your classwork will determine how you do in the end on the exams. Now, you'll learn this in the next set of videos, but there is a difference between in the multiplication rules between dependent and independent events. However, the tree diagram, once you get it set up, you just multiply along the branches. So, and again, once this tree diagram is set up properly, you don't need to worry about whether those events are independent or dependent. Just multiply across those branches. And even though we're not going to talk about the multiplication rule for dependent events today outside this example, and so supposedly we don't know how to do it, I've got these values set up from past data, or I actually could have made it with past data, but I just made these up. And let's talk about what is a probability in this example of a student passing the exam. Well, there's 2 branches that will make that happen. Do well and pass, or not do well as far as grade-wise goes, and still pass. So there's 2 tracks that will lead to that passing score. Now I'm going to use some of the rules we'll cover here in a minute at the end of the video, but I can only fit so much on this camera screen, chalkboard, so you'll just have to rewind if you want to replay this. The chances of passing, well, when you set up a tree diagram, you multiply along those branches. So doing well and passing is 0.4 times 0.9. And then you also have the probability or the chance of not doing well but yet pull it out at the end, and that's 0.6 times 0.3. Now you can't run along these 2 tracks at the same time, so in a few minutes when you see rule number 3, which is the probability of A or B. The probability of A or B is equal to the probability of A plus the probability of B if those events are disjoint. And you cannot, that means they can't occur at the same time, and you cannot go along both of these branches at the same time. There's 2 ways to pass the exam, but you can't do poorly and great in the same class at the same time. So those are disjoint events. So we multiply along the first set of branches, the second set of branches, and then because they're disjoint, we can simply add those probabilities together and have our answer. That's going to be 0.36 plus 0.18, and that is equal to around 36, 46, 54%. And Hopefully my seniors get a little bit less senioritis this year. Hopefully these videos are helping them as well as I hope they're helping you guys who are watching in YouTube land. And I'm not saying that's my overall passing rate, but of course I am hoping they're a little better every year I teach the class. Multiplication principle. It's kind of what I did here with this tree diagram, but not exactly. If you want the total number of combinations, you multiply the number of outcomes for each trial. If you flip a coin twice, that's 2 outcomes for the first throw, 2 outcomes for the second toss, and that's 2 times 2 is 4, so there's 4 outcomes. If you roll 2 dice and you keep track of the order that those outcomes come out, well, that's 6 times 6, which is 36 outcomes. If you want to really get depressed about your chances of winning the lottery, whatever state you're in, well, how many numbers do you get to choose? How many numbers do you have to choose? And multiply that together and you'll see how many different combinations of those numbers there are to win the lottery. Now, it won't exactly come out to your probability of winning the lottery, but it'll make you realize just how many possibilities there are when you pull out 6 numbers from a tub, and I don't even know how many numbers our state lottery has, maybe 50? At any rate, if you want the number of combinations, just multiply down. You're building a car and you got 2 choices for color and 3 choices for engines. It's 2 times 3, that's 6 possibilities. Alright, moving on to the next screen. Woo! No. Alrighty then. Now, this idea of independent trials, sampling with replacement. This is not generally done in like real world sampling, like you set up a sample or choosing items for an experiment, whatnot. But sampling with replacement, pull numbers out of a hat, record them, and replace them. The next trial will be independent since all the numbers are still in the hat. Or think of it as a deck of cards. If you have a standard deck of cards here in America anyway, it's hearts, spades, diamonds, and clubs, and there's 52 cards in the deck. So the chance of a heart is 1/4. Well, if I have a deck of cards and it's all shuffled and I pull one out randomly and it turns out to be hearts, the chance, and if I keep that card in my hand, the chance of the next heart is going to be lower. It's going to be, I think, 12 out of 51 instead of 13 out of 52. Well, if I put that card back in the deck and reshuffle it, then my next pull out of the card, out of the deck, is going to be independent because I've replaced what I've pulled out and recorded, so my chance of the next heart is going to be the same. Sampling without replacement is pulling numbers out of a hat, recorded, and then you keep it. Pulling cards out of a deck, I got a small deck of cards, again, 1 deck of cards, I pull a card out, it's hearts. Well, the chance of that first heart was 13 out of 52. Now, if I hold it in my hand, the chance of the next heart is only going to be 12 out of 51. See, the probabilities have changed a little bit. That means my next trial would be dependent. The next outcome would be dependent on the first result. If I pull a heart out, that lowers my chance of the next card being a heart, and so on. Or if I don't pull a heart out, the next card is more likely to be a heart. This dependent setting can be considered independent if the population is over 10 times the sample size. I cannot stress how often we are going to use the phrase, the population needs to be over 10 times the size of the sample. This many settings, such as this, you're doing quality control at the end of an assembly line, there's 50,000 units being produced, you're pulling 50 of them out to make sure that they're, as high quality as the company expects. Well, if you pull a bad item out and you hold it, you have technically lowered the probability of the next item being faulty. So that's not mathematically, in a pure mathematical sense, that's not a independent setting. But as long as the population is over 10 times the sample size, we can kind of cheat that and say it's close enough to be independent for the purpose of statistics. And I don't know about more advanced statistics, but we will only in Intro to Statistics be able to work with data that came from independent trials or independent observations. So all these standard deviation formulas you're going to learn, and so far it's only one. It's what your calculator does when you do 1-bar stats. S of x equals the square root of 1 over n minus 1 times the summation of x of I minus the mean of x squared. even that simple formula and all the other ones we're going to learn eventually will only work if the observations or if the data is from independent observations or trials. So in a lot of settings in reality are not truly independent. So this phrase will be repeated many, many times through the rest of the chapters of this textbook that allows us to assume independence even though our setting, like quality control at the end of an experiment, at the end of an assembly line, truly is not. Alright? Woo! Moving on! Alright, let's start over again. Your probability rules, your 5 basic probability rules that you'll start off learning in Intro to Statistics. And indeed, a lot of math books will have these. I just said this in the previous video, but if you happen upon this one, let me go over it again. Probability of A, the probability of any one singular event is going to be between 0 and 1, and it can be 0 and can be 1. If the probability of an event is 0, that means that there's no way it can happen. If the probability is 1, it's guaranteed to happen, and then there's everything else in between. If S is the sample space, all of the possible outcomes and the variable of interest that you're looking at, the probability of that entire sample space is equal to 1. In the previous video, or now it's the previous video, I set up a sample space for rolling a die and looking at the number of dots that came up. And it's a pretty simple example, just 1 through 6. And each outcome had a 1/6 probability. Well, as long as I list off the entire sample space, and as long as the probability of that entire sample space is 1, that probability model is valid. So, there's the second rule. I'm going to skip 3 for a second. Identity 4, the rule number 4 is the complement of an event A is that A does not occur. This rule is going to help us solve, for a few questions, what could be potentially some really difficult questions, but if you understand the idea of complements, you can use this, well, the opposite of this occurring is this occurring. That's going to be helpful, and I'll have some time since I'm doing part 3 to erase some of this and give you an example of that. So the complement of an event A is that A does not occur, and the probability of a complementary event, A with the C exponent, is equal to 1 minus the probability of that event occurring. Okay, now 3 and 5, you might heard in an earlier math class, one where they're really not talking about probabilities very much, just barely touching on it. We like to say OR means add, AND means multiply. You got some bag of marbles, red and blue. What's probably, red, blue, green, white, whatever. What's probably equal a red one or a blue one out? Well, those events are disjoint. There's no way a marble could be blue and red at the same time. So we just go, well, you just find the probability of red and the probability of blue and add them together. Well, you don't need to stress the fact that they must be disjoint events in a real basic math class that's just touching on probabilities. If A and B are disjoint, no, I guess what I'm saying is you've heard this rule before, but please focus on when you can do these rules. That is going to be what's picked apart in your multiple choice questions on an AP test. Statistics. If A and B are disjoint, mutually exclusive, same phrase, different phrase, same meaning, if they have no outcomes in common and so can never occur simultaneously, the probability of A or B equals the probability of A plus the probability of B. I'll be doing a lot more discussion about Venn diagrams in a later video, but this is an example of what a Venn diagram would look like if the events are disjoint. 0 overlap between them. They cannot occur at the same time. I know this is a very simplified example, but flipping a coin. You cannot get a coin to land heads and tails at the same time. If you have a bag of solid colored marbles, you cannot pull that red and blue out. You can't pull a marble out that's both red and blue at the same time. Now, disjoint events are dependent events. Think of a coin. Let's think about independence. Independence means that we've had independent trials, like take this coin. When you flip a coin, it lands, you pick it back up and flip it again. That next trial is going to be independent. But as far as the actual outcomes, when you flip a coin and it's in the air and it lands, there's 2 possible outcomes. Now, those outcomes of heads or tails are disjoint. You can't get both to show up at the same time. So if heads shows up, it's preventing the possibility of tails showing. If head shows up, it prevents the possibility of tails showing up. That first outcome showing up is affecting whether or not the second outcome shows up. You see how that's not independent? Independence means that one outcome does not affect the probability of another outcome showing up. So, disjoint events are automatically always dependent. However, that phrase does not work in reverse. Dependent events are not automatically disjoint. Like if I'm talking about people, maybe some use a pretzel. Well, use a pretzel. You go to a bar and you're looking at people's eating and drinking habits, and there's some stuff on the bar like pretzels. And then there's, whether or not you have a drink. Well, first of all, you go to a bar maybe to have a drink. Secondly, if you're eating pretzels, they're salty and they'll make it, make you thirsty and make you want to drink more. So those are probably not, there's a mathematical check for it. We're not going to be able to do it in this video as an example, but I think we can understand, theorize that eating salty snacks is going to make you more likely to have a drink or an additional drink. So these events are probably dependent. These outcomes are probably dependent of each other, yet they can't occur at the same time. I mean, some people only have a drink. Some I could imagine just taking a snack for some reason and not having a drink. And of course, there's going to be people that do both. Well, what did I say here? Disjoint events are dependent. However, dependent events are not automatically disjoint. I'm trying to give you an example where it's conceivable that those two events are dependent, but yet they're not disjoint. That it can occur at the same time. So disjoint, dependent, but dependent does not automatically mean disjoint. The last rule, if A and B are independent, then the probability of A, this says and, the probability of A and B is equal to the probability of A times the probability of B. Depending on what information is given, this can be a mathematical check for independence. And since I've got some time, let's maybe just make up some stupid numbers here. Let's say the probability of pretzels is 20%. The probability of having a drink is 0.75%. Well, if those were truly independent events, then the probability of somebody having both would be 0.2 times 0.75, which is 15%. .75 times 0.2 is 0.15. Well, that would be assuming that they were independent. But then if I come along and I go, hey, the probability that somebody eats pretzels and has a drink is 40%. Well, I told you pretzels were 20%, or maybe you observed it. Drinking was, having a drink was 75%. If they were independent, then I could just multiply those together and get the probability of both occurring. And of course, I just made these numbers up, but based on my numbers, that would be a 15% probability. Well then, if we're told in the question that the probability that somebody actually has both of those items, and that probability doesn't match, that probability is maybe 40%, then our conclusion would be, well, this rule only works if the events are independent. Well, if I did the rule and I didn't get a matching answer, 15% doesn't equal 40%, then I just shown with a little mathematical check that those events are dependent of each other. Alright, so I did give you an example. I didn't expect to have the time to. Okay, let's take a look at this rule here and see if I can get an example done before my alarm goes off. Got to give myself some room to write. Okay, so let's say, didn't expect to do this on video, so I got to think about this here. We're having 4 kids. And we're talking about the probability of X is number of boys, and I want the probability that X equals 0 out of those boys. That X equals 0 if you have 4 kids. So we're going to have 4 kids, we're up to 4 kids, and we're just going to have 4 kids. X is the number of boys. What's the probability that you have no boys? Well, that's going to be, well, we have a girl. Probably should have picked an example where it wasn't 50-50, so you could tell if it's talking about a girl or a boy. But we have a girl. We have, not a girlie, but a girl. Then we have another girl. And another one. And another one. So the probability of 0 boys is going to be 1, 2, 4, 8, 16. So there's a 1/16th chance that if you have 4 kids, you have no boys. Well, what's the probability of, well, I can come up with all kinds of questions, but a lot of the questions I come up with are going to require skills that we'll learn in the next chapter, not now. So what would be the complement of 0 boys? Any idea? It's not 4 boys. The complement of no boys is at least 1. So the complement to no boys in your family of 4 kids is at least 1 boy out of your 4 kids. Now, if you wanted to analyze this question, you would have to find the probability that X equals 1, that there's 1 boy out of the 4. And then the probability that there's 2 boys out of the 4. And then the probability there's 3 boys out of the 4. And the probability there's 4 boys out of the 4. And it's a fairly simple example, so you can probably do that after a certain number of time and steps without really knowing the proper formulas to do it and the process. But since at least 1 boy is a complement to none, and we already have that answer, then the probability that X is at least 1 is simply 1 minus 1/16 or 15/16. So, kind of a quick example of how complements can allow us to solve some probability questions that the way this question is worded would honestly be a lot of work if you did not first find the probability of the complement, or in this case, none of the 4 kids having a boy. I'm Mr. True. I hope I've helped. If you appreciate my efforts, please spread the word on my new budding channel. Let me know if you have any questions. I'll try and help you out. Read your book. Go do your homework. I'm Mr. True. I'm out.